which next slide, which includes myself, Savannah from the Harvest New York Cornell Cooperative Extension Team, Allison, Kayla, Kristen, and Aaron, who will be joining us later on in this presentation. Next slide.
Okay, so I'm going to kick us off on our content, and I'm Allison Chaltherchan, and I work at Cornell University with the Cornell Climate Smart Farming Program, the Urban Camp Program, and the AI Leaf Institute in CALS, the College of Ag and Life Sciences. So last session, if you remember, Savannah gave us a very detailed coverage of all the ways that climate change is impacting agriculture, especially agriculture in the northeastern United States. And so, if you remember, we kind of summarized that to be that there are both challenges and opportunities for agriculture because of climate change. The challenges include that we already see significant increases in temperature, and that is causing heat stress in both livestock and crops. We see short-term drought, and as well, we see increased precipitation. And you can say, why do we have both increased precipitation and short-term drought? It's because the way that we are getting our precipitation is in these heavy rainfall events or extreme rainfall that can cause flooding. And in between those events, we see increased temperatures, so more evapotranspiration, which can cause drought. So both of those issues, temperature increases, extreme precipitation, and drought. And then in addition, we see that there are changes in pests and disease pressure because of this temperature increase and changes in precipitation, humidity. It's allowing new pests and disease to thrive in the Northeast. And then one of the things that farmers tell us most clearly is that climate change makes the growing seasons more variable and uncertain. Like what you're seeing this year, what you're going to plan for this year as a farmer, you're not certain that it's going to be the same as last year. So the opportunities, though, are we will in the Northeast, we will have adequate water in the future. With the projections of climate change, we will see increasing precipitation. However, that's really challenging to manage. And so we have to manage that water carefully. We have to store it, or we have to make sure that it's not causing runoff or flooding. We're also going to see longer, warmer growing seasons. We already see that. And so farmers can actually grow different crops than they used to, or maybe do double cropping. We see shifts in productivity elsewhere. So elsewhere around the world, as there are impacts to agriculture, that may mean that if a tomato crop is lost in California, we may have opportunities to grow more vegetables under greenhouses here because there's losses elsewhere. So we have a potential to expand and diversify markets. And right in the New York City area, metro area, we have 22% of the US population. Hard to believe. So if we think about it, we do have a lot of opportunities to expand production sustainably, in part because of climate change. So that gives you a little overview. And now we're going to turn to this concept of adaptation. So how do we respond to those impacts that we just talked about? So what is adaptation? We often hear this term when we talk about climate change. And really, we should think about it as the process of adjusting to actual or expected or projected climate change and its effects. In human systems, adaptation seeks to moderate harm or exploit beneficial opportunities that we just talked about. In natural systems, human intervention may facilitate adjustment to expected climate and its effects. So really, adaptation is being aware of the climate impacts and the projected impacts in the future, and then adjusting your farm practices, your farm operation to lessen the harm, lessen the risk, or take advantage of opportunities. Next slide. So we want to make sure that you're aware of the difference between adaptation and mitigation. And we often talk about mitigating the harm by adaptation. But in reality, when we talk about mitigation or when it's talked about in climate science community, mitigation really means reducing greenhouse gas emissions. And so that's tackling the causes of climate change rather than the consequences. This involves either reducing our emissions of greenhouse gases or capturing, enhancing carbon sinks. So storing carbon in the soil, for example. That's the opposite of adaptation, which is really reducing the vulnerability of natural and human systems to the impacts of climate change and adapting to a changing climate through adjustments in our social systems, our ecological or farming systems, or our economic systems. So, two different concepts. Next slide. And you can think about that in terms of just some simple examples of how would you think about adaptation versus mitigation, specifically for agriculture. For adaptation, again, you want to reduce the impacts or make your farming operation more resilient. So in this picture, you see uh, hay in rows, using no-till, using cover crops to make sure that there's less soil erosion. And then where you might see heat stress or disease pressure in vegetables, you might want to think about if you're adapting to switch to a more disease resilient crop. That is all part of adaptation versus mitigation. This is just an example. Some farms have installed solar panels, and by doing that, they're reducing their energy use. They're reducing their use of fossil fuels, which emit greenhouse gases to the atmosphere. Okay, next slide. And one way I think it's really important to think about these two concepts is maybe people would say it's more important to adapt to climate change. And for agriculture, that's certainly the case because farmers are on the front lines of climate change, and we really do need to adapt. We need to make our farms more resilient. But we can't just adapt ourselves out of the problem. And what do I mean by that? That means if we don't also reduce emissions of greenhouse gases, the climate is continuing to change. Temperatures are going to continue to rise. There's going to be more extreme rainfall, and that's going to make our problems on our farms more difficult. We're just going to have to adapt more. So really the best thing to do is to mitigate and adapt at the same time. And you can kind of see this in this graph. It's kind of a cool graph. As you see mitigation, it's reducing greenhouse gas emissions on the left-hand side, and it goes up. It reduces greenhouse gas concentrations that will reduce climate change, reduce impacts, and the need for response. So it makes it so that we don't have to adapt as much. Okay, next slide. In reality, though, especially in agriculture, these concepts have some overlap. And what do I mean by that? I love this Venn diagram because it shows you adaptation on the left-hand side. And so, kind of some of those practices we talked about to increase resiliency on farms would be improving water management, right? You're going to get those short-term drought. You need to respond or adapt by improving your water management storage capacity. You need to diversify your crops or your livestock production to respond to heat, extreme weather preparedness or planning on your farm, or infrastructure improvements. Those are all adaptations. For mitigation, examples again would be installing solar panels, improving nitrogen use efficiency so you're not emitting nitrogen into the atmosphere, which is a strong greenhouse gas. But in reality, there's some overlap there. So the best thing that we can do as farmers is utilize practices like agroforestry or conservation tillage or cover cropping that both help with adaptation and mitigation. So, Savannah, could I ask you to like explain in a little bit more detail how agroforestry helps with both adaptation and mitigation?
Sure thing. So agroforestry helps with both adaptation and mitigation because you're growing permanent crops in the ground, usually trees that are very woody and good at storing carbon in their tissues. So therefore you're mitigating because you're drawing carbon out of the atmosphere and storing it long term in the cells of those trees. And it's an adaptation practice as well because oftentimes folks will grow crops in the understory of the trees, for example, that provides a shading benefit when you have extreme heat. Yolanda will talk a little bit more about that later on. So you're getting both those benefits there. And it's a similar story with conservation tillage and cover cropping. Both of those practices increase carbon storage in soils long term, but you also get an adaptation benefit because both those practices oftentimes increase the ability of soils to hold water or
Hmm.
to reduce erosion. So that's where you're getting those knock-on effects. And I'll just add that some folks might argue that application of rock dust or biochar is adaptation and mitigation because that practice can also increase water holding capacity, but we just put it over in mitigation this time because really a huge benefit of those two practices is that it does store an immense amount of carbon in the soil, but in a very long-term storage form because it is creating pure carbon that doesn't
Mm,
degrade easily. So.
cool. Excellent. Okay, next slide. So, when we think about adaptation measures, the goal on farms may be different for different farms. And so, on our urban farms, adaptation may look very different than on a large dairy farm in upstate New York. And those goals may, each farm operation may have different goals. Their main goal may be avoiding risk. So, they may want to avoid the risk that they're going to lose an entire crop if they get extreme rainfall, or reduce risk, or just accept some level of risk. And then they may want to really take advantage of opportunities that we talked about, grow different varieties. If they experienced heavy losses due to drought or heat stress the last summer, they may want to think about, well, I'm going to try this new crop and take advantage, maybe a specialty crop. And then another goal is just improving preparedness, doing a planning process. Next slide. So when we think about reducing risk, I love this graphic. It's pretty cool. It comes from the Intergovernmental Panel on Climate Change. And you see that risk is in the center of these three other elements that all contribute to risk. And that those are vulnerability, the hazards of climate change, and the exposure. So when you think about your farm, one way to think about the level of risk is how vulnerable your farm is to climate change. Is it right near the Long Island Sound? And so it's very vulnerable to storm surge. Or is it vulnerable to climate hazards? Again, maybe the storm surge or saltwater intrusion on a farm. The hazard might be different or more extreme on some farms. And then the level of exposure. So if you're a farm up on top of a building, um, and you've got a lot of exposure to um, high winds, your exposure is very different from another farm that's at ground level. So these different levels of vulnerability, the different climate hazards and exposure all lead to different risks. And we can control exposure and vulnerability to some extent. It's harder to control the hazards. And the way that we control exposure or vulnerability is through adaptation. Next slide. The other way of thinking about adaptation in agriculture and urban farms is that it's very site specific and it's local. And what do we mean by that? Again, unlike maybe mitigation, adaptation is going to vary significantly by the type of commodities you're growing or the geography of where your farm's located. And so we can't say that adaptation is, we can't give you a one size fits all plan for adaptation on your farm. It's going to be very, very specific to what you're experiencing. So, for example, when we've thought about this to try and help farmers plan in New York State, we thought about it in terms of the different agricultural commodities that are primarily grown in New York State, and then the impacts to those specific commodities or operations. So for vegetables and field crops, like the climate change impacts are very different than the impacts to dairy and livestock. And for vegetables and field crops, the climate impacts that are most significantly affecting those crops are diseases, weed and pest pressure, flooding, and short-term drought, longer growing seasons, and then heat stress. And the way that we adapt is we have to have very specific tools or adaptation practices for those specific impacts. And again, if you look up and down that chart, the adaptation practices you might adopt for growing vegetables in New York City are going to be very different than if you're adapting on a large barn. Okay, next step. And so, how do you manage that? How do you manage planning for adaptation on your farm that's going to be very different from other farms? Well, you need to go through a planning process, and there are many different tools out there. The one that we like is very comprehensive, and you can find it on this link here. And it's called the Adaptation Resources for Agriculture for the Midwest and the Northeast, responding to climate variability and change. Next slide. So what this guide does is it actually walks a farm through this menu and this stepwise process for thinking about adaptation planning. And so it's pretty straightforward to really think about these different functions of soil and water, to think about crops and livestock, reducing risks, reducing impacts of extreme weather. So adopting different strategies for all these impacts. Next slide. Okay, so when we think about identifying farm vulnerabilities and associated risks, we think, and then this is just another way of maybe thinking about that graphic. So on the left-hand side, we have climate impacts. And again, the farm vulnerability of your particular farm and where they intersect is that risk. So again, the vulnerability is the weakness in farm or farming systems to observed or projected climate impacts. And then the risk is the potential for loss or damage to farming operations or systems. And that can be like physical loss, losing a crop, or economic loss, having your entire barn collapse under the weight of snow is an example of a huge economic loss, or having to purchase forage for your animals when you've lost your crop from drought. Next slide. So another way of thinking through that adaptation process, this comes from that same guide. And I really like this because it's a stepwise, really rational process where the first step is really defining your management goals. Then the second step is assessing what are those site-specific impacts on your farm, because they're going to be different. So is your farm, are the most important impacts the flooding that you get on one area of the farm again and again because it's a low-level area or the soil's really poor there? Or is it a different climate impact that's really causing a lot of stress on the farm, loss of income, And so you want to assess that and identify what are the most important impacts that you want to address. And that's part of step 3. You want to evaluate those impacts along with your management objectives for the future, given the impacts and the vulnerabilities. And then you want to identify the specific adaptation approaches that will help address those and the tactics for implementation. And then you want to start implementing. And then step 5 is always after the growing season, maybe monitor. Maybe it takes 2 growing seasons, monitor what was the cost of making those changes? What was the value? Did you see less flooding? You want to evaluate the effectiveness of those implemented actions. Next step. This is just another version that we've used with this program and with the Northeast Climate Hub. Again, you want to assess the risks on the farm, identify options, maybe assess the trade-offs. Like, are you going to spend money on improving your infrastructure, or are you going to maybe spend a little less money trying a different cultivar or type of crop? You want to then choose the best of those, or what can you manage to take on in this year? And then you want to implement those changes, monitor and assess them, share ideas. Always good in that process. Learn from what others have done, and then revise the approach and maybe try something slightly different for the next season. And I guess I want to say overall, the purpose of planning is so important because you don't want to start just adopting a practice to respond to these increasing impacts without thinking it through, because maybe that's not the best thing that you should be focusing on. And we always like to say, like, you can't start planning or changing things until you've assessed the situation. Okay, so that's that concept that a plan, it's very important to start with a plan before you start making changes to adapt to climate change. Next slide. Again, this is the planning process that we provided to you, along with a booklet and another resource. We can make all these resources available on our website. There's another great planning tool from Laura Legnick, and it's again assessing risks, identifying the options for adaptation, implementing those, and then monitoring them. Next step. I want to end up by talking about this larger maybe concept of climate smart agriculture, which is so important. We can think about adaptation as one part of this. And this term is becoming really important in the United States and globally around the world. Many countries have climate smart agriculture plans, and they've received funding or grants to implement climate smart agriculture in their country. And many farms in the US actually got a lot of funding through programs like this from USDA. And what do we mean by that? It's a 3-pronged approach because we know that mitigation is very important. Agriculture does contribute significantly to climate emissions globally and in the United States. We also know that farms in the United States and around the world are getting hit by these impacts. And so we both need to reduce agriculture's contribution to climate change through mitigation. That's on the lower right. We need to adapt sustainably, strengthen resilience to climate change and variability. And the third thing is we need to sustainably increase productivity and income for farmers. If other parts of the world are going to be facing more severe climate impacts and have a more difficult time growing food, then our farms in the United States can sustainably increase our productivity to grow more food. So that is that really important concept of climate smart agriculture. Everything that you're doing on your farm is contributing to these global goals. Next slide. So one of the tools that we've developed from Cornell University are these free online decision support tools through our website, and you can just Google, or it's climatesmartfarming.org. And these tools are free and they're available to use anywhere in the Northeast, and that's from Maine, any county in Maine, all the way down to West Virginia. And so if you click through there, Savannah, I'll just introduce them really briefly. The way these tools work is they take weather data, both long-term weather data and forecasts from the National Weather Service. This data is maintained by Cornell University through the Northeast Regional Climate Center. And we take that climate data and we display it for you in 4 by 4 kilometer gridded data sets. So what you do actually, if you look on the left-hand side, when you use these tools, you can actually enter your location, including a farm in New York City, an urban farm. You enter your exact zip code or your address, and then you enter some of the tools, you enter some other data, and then the tool is going to take that data and that location and combine it with the long-term climate data and the forecast data for that specific area. So these tools are super cool because they're very specific to your farm. Often the farmer input can be what's the planting date, what's the crop you're growing, and you can choose to look at the data for this season or going back to many seasons. So we'll go to the next slide. One of the most useful of these tools is called the Growing Degree Day Calculator. And this tool, we actually chose the location here for Governor's Island, and we chose the 2024 growing season because when we're recording this, the current growing season hasn't started yet. So you could choose the planting date. For Governor's Island, that would be about May 15th. And if you had chosen that date and you had been following this through in 2024, what you can see here is the entire growing season. And you can see that accumulation of growing degree days in that crop for the full season was way above the 15-year average for that season. And this is just an example of climate change, because if you were to go click through all the past years available for that specific location, you'd see very different year to year comparisons of how that crop is accumulating growing degree days. It's also just a very good tool for when you're in the growing season for understanding how that crop is growing and when it's ready to harvest. So it's not only good for understanding the climate change, but also projecting for the future. If you see how it's been going, you can kind of project for the future, but also a great tool day to day because this tool is updated on a daily basis. It's giving you very accurate information for your specific location. And we would say that using tools like this is an adaptation because you're using more precise data to inform your decisions that help you respond to the climate changes in climate. Next slide. Another tool here that you can use for free is called the Water Deficit Calculator. Again, I'm showing the data here for 2024 for Governor's Island. If we were growing in a soil which was medium loam, we were growing a grass type of crop, and we planted around May 15th. This is again showing you the entire growing season for 2024, that every time you see one of those dots, it's a rainfall event. And some of those are very large rainfall events that could, if you were in severe plant stress, it could actually recuperate the water in the soil so that the field capacity was up where it should be. But this shows that there was a lot of drought or plant stress because of water deficit in that 2024 growing season. And again, this is very specifically tied to the type of crop you're growing. So if you had put a different crop in the crop type, It might be different because different crops take up water differently, or the soil water holding capacity. So that is a great tool to use in the season to get a sense of what's happening. And if you use the tool in the season, there is a 3-day forecast. It's going to tell you, wow, I am actually in very likely my plants are facing water deficit or plant stress, but there is projected to be a pretty heavy rainfall event in the next 3 days. So maybe I don't need to worry about irrigation, but you can also click the box over there for irrigation and see, did that actually improve your water holding capacity in the soil? Okay, so perfect. I think that's one of the last slides. Next slide. Yep. I'm going to turn it over now to our team. Thank you.
Alrighty. Thanks, Allison. So I'm gonna take it over here and we're gonna switch gears a little bit. And we're gonna talk about climate impacts on urban farms. And as a review, we're gonna talk about climate impacts and the science behind their effect on plants and water. So the goal here is to understand why adaptation or mitigation are necessary from a biological standpoint. So we're going from plant cell up to the global scale. So just as a brief review, I think you guys have seen this before, but when we're talking about impacts to urban farms, specifically around heat, I've divided this out into 3 different categories: plants, livestock, and people. And as far as plants go, we'll talk a little bit more about this, but increasing heat usually increases plant water demand, which is an increase in evapotranspiration. That increases our need to irrigate. And then heat can cause elevated incidence of physiological diseases. And then when plants are too hot, photosynthesis is inhibited. We'll dive a little bit more into what that means today. And in addition to that, elevated heat can also reduce pollination efficiency in some crops. Pollen is inactive or is not fertile over some temperatures. So that might reduce fruit set in things like tomatoes, for example. Next, when it comes to livestock, heat leads to decreased animal comfort. And oftentimes in the city, when we're talking about livestock, we're talking about chickens. So heat stress reduces egg quality as hens struggle to regulate their body temperature, and that can result in reduced calcium deposition into the shell. And in addition to that, animals tend to eat less when they are hot. So that reduces overall yield there. And then last but not least, as far as our people go that are helping us out on our farm, we have to be sure to implement steps to monitor employee well-being because things like heat stroke can sneak up on you really quickly. And then generally, folks who are hot tend to be less productive. I know I am when it's hot outside, not moving as quickly as usual. And then one other side effect can be that folks who are heat exhausted or overheated can be a little bit less, paying a little bit less attention to what they're doing, and that might lead to an increase in injuries. Work schedules might need to be shifted during heat waves to work during the coolest part of the day, so that might mean coming in much earlier than usual. And then you got to be sure to implement regular water breaks to avoid dehydration. And just briefly, precipitation. Allison covered a little this earlier, but flooding is always a problem when it comes to livestock, plants, people. An increase in leaf wetness in plants can also lead to an increase in disease incidence. And then standing water more generally can lead to plant death in some cases. So we're expected to see an increase in the number of extreme precipitation events. Um, but just because we're going to have adequate water, that doesn't mean that we're going to get out of this issue of having drought. That means that water is going to fall in more extreme incidences that are also marked by longer periods of no rainfall. So we need to have a plan in place to collect that water so we can use it later on in the season when we have a deficit. And then a projected increase in spring and fall rainfall can lead to a delay in planting and harvest. So, um, you can't really get around that one very easily, but having plans in place to help you be a little bit more flexible if you're having to delay planting more long term is always a good idea. And this is maybe less of an issue on urban farms because you're not having to move heavy equipment onto a field oftentimes. But it's just one thing to be aware of. As far as livestock goes, if your animals are standing out in mud, that can lead to some issues with infections on their feet. So being sure to provide an area for them to get out of the mud is essential. And then making sure that you have mapped and understood where the water runs through their area when you have flooding events is important because sometimes during these big deluges, we just get water maybe in areas where our chickens are that we're not used to having it. So going out there and checking on them regularly if you're having an extreme event and you're able to safely do so is really important. Then people, it can disrupt work schedules. Slippery surfaces can cause an increase in workplace accidents. And then being sure to check areas where folks are working a lot to make sure that there's no mold occurring is important because that can lead to an increase in respiratory illnesses in some folks. And then another important thing is that if you have an increase in precipitation or extreme flooding, just be cognizant of the fact that folks might be coming from different areas of the city, for example, that might be more impacted by flooding and being flexible on, if they come into work or not that day. And then we have extreme weather. So this is kind of broken out into three different subcategories within these categories. We're talking about high winds, hail, and hurricanes, and just kind of generally high winds can cause damage to plants. So that can either cause the plant to fall over or break. And those areas with breakage are oftentimes excellent sites for disease to infect our plants. So being aware of that and trying to make sure we have adequate plant support before these high winds come through is really important. So we're not getting that knock-on effect of creating great sites for disease to enter into our plants. Another thing that can happen is that loose tarps or row covers, when they're flapping around in the wind, can also cause breakage, which, yet again leads to more sites for disease. And then if you have a soil that has a lot of very light portions, like for example, a lot of farms in the city have high organic matter, if it's not adequately moist or adequately covered, if you have really high winds, those portions could potentially blow away. So be aware that that issue could arise. And then high wind also increases evapotranspiration. Hail can destroy the ability of you to market some of these plants and also creates more sites for disease to enter. And then hurricanes, all the above plus flooding. With livestock, high winds can cause stress in animals. If structures aren't appropriately secured, those can blow away, causing loss, injury, or death of your livestock. Hail can kill or injure livestock if it's not under cover. And then hurricanes, same thing. Making sure that livestock are appropriately secured and have access to high ground is really important during those types of events. Then people, high winds can start blowing objects away around that could injure employees, can cause stress to folks. An example of this would be to make sure that your high tunnels are really well bolted down in case of these types of events. That's happened before where they've blown away during one of these extreme wind events and injured people before. So just being aware that that can happen and making sure we have lots of bolting into the ground there. And then hail can damage personal property or injure individuals. So making sure that you have good shelter that employees can get underneath if you're worried about hail, very important. And hurricanes, same thing, but flooding can cause injury to personnel. So now that we've talked about that a little bit in review, we're gonna switch over to talking a bit about the science behind adaptation. And one of the first things that we're gonna talk about is photosynthesis. So just as a brief review, you can see these equations here that talk about the process of photosynthesis. So photosynthesis is when plants take carbon dioxide, water, and solar energy and convert that into glucose and oxygen, and the glucose is used to fuel the plant's activities. So one other way to think about that is that we have photosynthesis on the top side. So we're taking carbon dioxide and water, and we're making energy and oxygen. And then the opposite of that is cellular respiration, which is what animals do, but plants also do it too, just on a much smaller scale. When we're taking oxygen and glucose, and we're making water and carbon dioxide. So photosynthesis, it really relies on the stomata. So here we see the stomata on the plant. They look like this. This is how they look when they're open. This is how they look when they're closed. You have these two guard cells that are on the side of the stomata, and they regulate whether the stomata is open or closed. And that happens, and the closure happens because the plants increase the Tudor pressure within these guard cells, and that leads to the closure of the stomata. So, one thing that's important to note about stomata, or you can kind of think of them as the nose of the plant. They're enabling the plant to bring in air from the outside or close off so that they're not losing air from inside the plant. And one reason why that's important is because you see the stomata here at the bottom. It's facilitating the exchange of air from outside the cell of the plant to inside of the plant. So air generally outside the plant is going to have a higher concentration of CO2 than of oxygen. So CO2 is going in when the stomata is open and oxygen is leaving. And why are we having higher concentrations of oxygen within the plant in those areas? That's because we have this area in here called the mesophyll, which is made up of two different types of cells. Oftentimes, you have the spongy parenchyma or spongy mesophyll, and then you have these palisade parenchyma or palisade mesophyll cells. And the function of the spongy parenchyma is to be really loose. You can see an image of it here. It's very loose. There's lots of space for air to diffuse in and out. And so in these cells is where gas exchange is happening within the cells. So these cells are taking in CO2 to facilitate photosynthesis. And during the process of photosynthesis, we're releasing those oxygen molecules, and those are exiting out of these cells and then flowing through the stomata into the environment. And most of the actual photosynthetic reactions, those are occurring in these palisade parenchyma cells that you can see here, or palisade mesophyll. And then we have the epidermis and cuticle, which are serving to protect the plant from outside impacts. So this is a borage plant. It's a C3 plant. We'll talk a bit more about what that means in a second, but it's basically doing regular photosynthesis, or the most common form of photosynthesis that plants that we interact with do. And another thing to take note of is there are two different types of reactions that are occurring when we're having photosynthesis. So there are reactions that depend on light, and then there are reactions that don't depend on light. And we'll dig into that a bit more here in a second. So why do we care about photosynthesis so much? And what is this enzyme that's facilitating the capture of CO2? So there's this really important plant enzyme called rubisco. Its government name is ribulose 1,5-biphosphate carboxylase oxygenase. Okay, that's a lot. But we'll talk a little bit more about what that means. So we've discussed the fact that the plant has stomata, which facilitates the diffusion of air into the plant, and the plant has the ability to close those stomata. So when a plant is happy, the stomata remain open. And if the stomata are open, that means that we have a higher concentration of CO2 within that spongy mesophyll that we discussed earlier. And usually the plant's happy when the temps are cool. It's happy when it's daytime because it's able to do photosynthesis then, and so the stomata are open then. And then under these cool temperatures, rubisco can tell the difference between oxygen and CO2. So it's able to differentiate between these two compounds. When a plant is stressed, so that might be when it's hot, for example, or at nighttime, some plants will close their stomata, not because they're stressed, but because they're not doing photosynthesis. They'll close their stomata to conserve water because when their stomata are open, not only are they losing whatever or facilitating the exchange of whatever gas is within the spongy mesophyll, they're also losing water out of these holes. So it will close the stomata to conserve water. And if the stomata are closed, there's going to be a higher concentration of oxygen in the spongy mesophyll because the plant oftentimes is still doing photosynthesis. So there's going to be more O2 molecules floating around in there than CO2 usually. So under these hot temperatures, Rubisco struggles to differentiate between oxygen and CO2. So if it's above 95 degrees Fahrenheit, Rubisco kind of becomes confused. It becomes less efficient and able to do its job. Why does this matter? That's because Rubisco's whole job is to pick up carbon atoms and fix them into energy. So now we're going to talk a little bit about photorespiration. So when a plant is normally undergoing the Calvin cycle, which is the light-independent reaction, it's going to gain 6 fixed carbon atoms when going through this whole cycle. So we don't really need to pay too much attention to what's going on here, except that the plant's going to have 6 CO2. Rubisco comes into act, and through this process, it is making 1 glucose that it's going to use for energy later on. And so the net effect here is that this plant fixed 6 carbon atoms into glucose that stays within its tissues and it uses to make all sorts of different compounds like carbohydrates, fats, all those good things that it needs to operate. But when we have this photorespiration occur when it's too hot and the plant's unable to, Rubisco is unable to effectively differentiate between oxygen and CO2, what happens is that Rubisco is still acting, but we have this salvage pathway that occurs where it's still making some sugars to help it undergo all the energy requirements that it has, but it's doing it in a less efficient way. So the net effect here is that we're losing 3 fixed carbon atoms. So the key takeaway here is that when the plant is heat stressed, Rubisco is less effective at differentiating between CO2 and oxygen, and that leads to a waste in energy and less carbon atoms fixed into the plant. So we are not effectively taking carbon from the atmosphere and putting it into our plant tissues. But this is an old problem, and over the many millions of years, plants have adapted ways to deal with this issue. So there are actually 3 different photosynthetic pathways that exist. And the way that they operate is either by separating the fixation of CO2 in space or in time. So most plants that we deal with are called C3 plants. So that's things like cabbages, carrots, many of our leafy vegetables are C3 plants, and they are best adapted to cool, wet environments. And these plants, they keep their stomata open during the day. And there's no separation of CO2 fixation in the Calvin cycle in space or in time. Then we have these other folk plants over here that have evolved some pathways to help deal with this issue, and those are called C4 plants. So those are things like grasses. Corn is a great example of a really common C4 plant, and it's evolved to kind of get around this issue by separating where these reactions happen. So instead of the fixation of CO2 occurring in the spongy mesophyll like we were talking about, it happens in bundle sheath cells. And these plants keep their stomata open during the day, and they're adapted to hot, sunny environments. Then we have cam plants, which are very unique. And they have separated out this process between night and day and time. So they have an acid that they've evolved that helps them facilitate these processes at nighttime. And the reason why that's important is because instead of having their stomata open during the day when it's very hot, very dry, and water would just be dumping out of the plant into the atmosphere, they're able to close their stomata during the day, harvest the light that they need to finish out this light independent reaction in the nighttime. So, these plants are usually adapted to very hot, dry environments, and examples of these plants are pineapples, but also when we think of these plants classically, we're thinking about cactuses, succulents, those types of plants. So just looking at this in a bit more detail, don't get overwhelmed by all the things flying around here, but it's just to show here we have this regular old C3 pathway. We have everything occurring in the same space, and it's usually occurring during the daytime when we have light pouring into the cells. We're making our sugars just using the Calvin cycle in same space, but over here we have the C4 pathway. So this is the process that is happening in the mesophyll cell. But then the plant's moving some of these metabolites out of the mesophyll cell into bundle sheath cells, which are adjacent to the mesophyll cell, where it's better able to control the concentration of CO2 and produce sugars out of this higher oxygen environment. So it's separated this pathway in space. Then we have the CAM pathway, and this is what's happening at night. This is what's happening during the day. So it's bringing in CO2 into the cell at nighttime to help, and it's putting it into acids or other organic compounds to help facilitate the process of making sugars during the daytime. So we're going to look at this video really quickly, and then I'll provide a few comments. Okay, guys, I'm going to have to go back and edit that because the sound's not working. Let me try to fix this. Okay, the sound's not working, but I've watched this a lot, so I'm just going to talk over it. Okay, so this is a visualization provided by NASA that helps you to visualize global carbon dioxide emissions. And this was created using satellite imagery. So I believe this is about a month in February a few years ago, but where you see the orange, that's CO2 that's going up into the atmosphere. Some of these smaller points are fires, for example, or there are factories that are producing a lot of CO2. And you can see that we're going to see a flashing effect here. So the flashing effect occurs because most plants are photosynthetically active during the daytime, and they're able to take in some of the CO2 out of the atmosphere. You can see right here in the tropics where there's a lot of rainforest, that flashing is really apparent. That's because plants are drawing that CO2 out of the atmosphere and using it to make energy during the daytime. So it's kind of like you can really see the lung action of those plants occurring here. Um, but yeah, I highly
Very
recommend
cool. Super
taking,
cool to see.
yeah, take the time to watch this video with sound if you can. It will provide a link in the comments so you can go see this video on NASA because they talk a little bit more about the methodology behind making this visualization, and they provide some really good commentary on what some of the spots you're seeing are. So, just to sum it all up here, science behind adaptation. How do plants adapt to handle these hot, dry conditions? And how can we capitalize on that? So some adaptations that an individual plant might take on are closing that stomata during times of extreme heat so that they're not losing all their water out of those pores. Additionally, they might change their leaf angle so that the solar radiation's not hitting it so directly and heating it up so much. This is really apparent in some corn varieties. Um, some of them have this adaptation called leaf rolling, and they're able to move their leaves so that they're not taking on so much heat when it's extremely hot. And then the plant itself might reduce its metabolic rate to slow some of these processes so it's not as active during these times of extreme stress. And then if the plant has adequate water supply, it's going to keep its stomata open, and that's going to invite in this process of transpiration where it's drawing water out of the soil profile through its body and out into the atmosphere to provide the cooling effect. But if we don't have adequate water, it will close its stomata to preserve water within the plant body. And then we have these adaptations that take place over hundreds to thousands of years, these evolutionary adaptations that the plants have brought on. One of the things that the plant might do is evolve a thicker, waxy cuticle. So all plants have some amount of wax on the outside of their leaves that helps to keep water in. But they might evolve a thicker cuticle to increase the efficiency of keeping that water in. They might evolve more efficient photosystems, like we discussed earlier. They might have smaller leaves, so there's less surface area for water to leave from. They can evolve hairy leaves, which also increases the ability of the plant to retain water. They might evolve deeper tap roots, which are able to get further down into the soil profile and extract water from a deeper depth, or they might evolve extensive shallow roots because that increases the ability of the plant to take up small amounts of water that are falling. So we might be in a situation where we're not receiving lots of very heavy rainfall events, but perhaps you're getting a heavy dew every morning, or you're getting very sporadic, tiny rain showers. Plant might have shallow roots near the surface that are able to harvest some of that opportunistic water. And then they might evolve more efficient stomatal closure, so they might improve the timing of when they're closing it, or they might be better at closing their stomata all the way. They could evolve improved water storage within the spongy mesophyll. So when we're talking about that, we're thinking about plants like cactuses or succulents that have a lot of space to keep water within those cells for use later on. And then they might evolutionarily evolve a reduced metabolic rate. That's different from the reduction in metabolic rate that happens in the individual adaptation. This might be something that evolves over many years to just improve the efficiency of the plant to operate under these stress conditions. So now we're going to shift to talk a little bit about evapotranspiration. We talked about transpiration a bit before. So transpiration, like I mentioned, is when the plant is pulling that available soil water out of the soil profile through its body and releasing it into the atmosphere. But evaporation is also occurring from the soil at the same time. So when we're talking about evapotranspiration, we're talking about the sum of transpiration from leaves and the evaporation from the soil. And these are all impacted by things like the external humidity and temperature and how much solar radiation we're receiving. So here's another long equation, but the things we really want to focus in on are air temperature and wind speed. So reference evapotranspiration, it's also called the Penman-Monteith equation. Really, it's taking in a whole lot of different factors to give us this just reference number for potential evapotranspiration, which is expressed in water volume evapotranspired in millimeters per day. Okay, so the two things that we care most about because they're most influenced by external conditions are air temperature at 2 meters height and then wind speed at 2 meters height. All the rest of this are interesting factors that go into evapotranspiration, but we really care about these two things because we're going to plug those in and it's going to spit out what the reference evapotranspiration is. So that's just a measure of how much water is leaving the soil, either through bare ground and going into the atmosphere, or is going through plants and into the atmosphere. And each crop has a different rate of how it's transpiring. So to correct for this, there are tables that have been developed, and that's called the crop evapotranspiration, or ETC. So we have our ETC, we have our ETO, and then we have this KC, which is listed here. I think it's dependent on how developed the crop is. So you can go through and find what your crop is. If it's lettuce, you're able to correct for what the appropriate evapotranspiration is to get to plug into, sorry, this equation here. So keep that in mind, but we're going to go back and talk briefly about potential evapotranspiration in the United States as we move forward through time. So historically, we're in the Northeast. Evapotranspiration in terms of millimeters of water loss per day is going to increase as we see an increase in climate change. Why is that happening? It's because we're projected to have increased heat in our region. And like we saw earlier, temperature and wind are two of the major factors that are affecting evapotranspiration. So we're going to move on, and we remember that ETC that we talked about, that crop coefficient that we calculated that took into account the reference evapotranspiration and also the maturity of our crop and the crop's individual unique characteristics. So we're using that ETC to calculate water balance, okay? ETC, we have evapotranspiration coming out here. When we're talking about water balance, we're talking about where the water is in the environment, and how are we affecting the the movement of that water. So we have our evapotranspiration here. We have any water that might come on from irrigation here. We have water that comes into our environment from precipitation over here. Then we also factor in water that's running off the surface here. And then we have water that's deeply percolating into the soil profile here. So there are two equations that kind of help us understand water balance. They're called the water balance equation. This is an unsimplified version, and this is the simplified version. But basically, you're taking into account all these different factors to help us understand where water is and where water is not. And that's able to transfer over and help us understand how much water we need to apply via irrigation to meet crop needs, okay, in this rooting zone. So another way to think about looking at that is through a water balance graph, okay? So that shows the balance between inputs and outputs. So if we have a wet season, we have precipitation that exceeds evapotranspiration. So we have a water surplus. And when we have water surpluses, that means that ground stores fill with water. We have more surface runoff because the pores that the water might go into when it's deeply percolating are already full. We have more discharge, so that means that river levels rise and pond levels will rise. When we have drier seasons, that means that evapotranspiration is exceeding precipitation. I would also say exceeding irrigation unless you're irrigating very heavily. So that means we have a depletion in the ground storage of water. So we'll have some flows into river channels, but it's not necessarily replaced by precipitation. And over time, that can lead to a decrease in groundwater, leading to a decrease in the levels of our ponds and rivers. And then when we swing back to a wet season, we're going to have a deficit of water because we've had this dry season going on, and that's going to enable us to recharge groundwater here. So this graph's a good way to visualize that. Here's potential evapotranspiration throughout the year. We see it's peaking in these hotter summer months and then coming down in the winter. in fall. And then we see this zone over here. This is where soil moisture recharge is occurring as we're moving into a season with more precipitation. And then, yeah, this is our water surplus over on the sides here. But this is just a good visualization of what we're talking about here with water balance, right? So water balance is really just a way of thinking about where the water went throughout the year. So why is this important? We want to understand what happens when water balance is off. So this is happening already in New York, specifically on Long Island. So this is a graph or a visualization that's made with satellites that are able to measure ground, um, the ground sinking. And that's happening because um, folks have a lot of wells on Long Island to provide water for their homes or to provide water for agricultural activities. And the rate of water withdrawal from the ground is actually higher than the rate of recharge from precipitation or irrigation. So what happens is that we can think about all these wells like mini straws that are penetrating into the soil and sucking water out of the soil profile. And it creates this drawdown effect. So we have this cone of depression here. We have where the water table would be, and then we have this cone of depression. And what happens there is that when you have these cones of depression, this negative area of pressure, there's all this ocean water surrounding this negative pressure. And so we get saltwater intrusion because salt water is being pulled out of these areas into these areas of negative pressure. And that's causing salt water to enter into our freshwater supplies here. So if we're not having adequate recharge, then we can have this problem occur in areas that are close to salty areas. All right, now we're going to move on to talking about adaptation strategies for urban farms.
Great. So just to talk about flooding in New York City and a few short-term strategies. One of them is bioretention or rain gardens, which are usually sloped, deep-rooted gardens that could be planted around urban ag sites, but they won't be appropriate if there's a high flood table. Another strategy are rainwater harvesting systems. And the EPA has a guide on that, along with Grow NYC, which has installed rainwater harvesting systems throughout New York City and also has a guide as well. Sea Grant is a great organization that has flooding experts if you want more information on that. But the photo on the right, photo on the bottom is a rainwater harvesting tank at Garden of Happiness in the Bronx. So next slide. And in terms of additional flooding resources in New York City, one of them is the Community Flood Project, which allows you to subscribe for alerts and submit flood reports in New York City. It helps to build legislation long-term for flooding solutions and something that's needed for future generations. So making sure that we're collecting that data so that we can help shape future policy. The LISS Resiliency Hub for Bronx and Queens County is also a resource. You can find helpful sites like the Reduce Flood Risk website on there, as well as grant writing assistance and other funding programs to make these projects happen for you, so long as you're in the Long Island Sound watershed, which is the Bronx and Queens counties. So wanted to make a shout out for those resources as well. Next slide. So like flooding, saltwater intrusion is an issue that we can mitigate with short-term Band-Aid strategies, but ultimately it needs to be addressed by county, municipality, or city government with long-term solutions and system upgrades. Luckily, it's not really much of an issue in New York City as we get water from our upstate reservoirs, but it is a big issue in coastal areas and Long Island. So I'll just mention it. Suffolk County in particular, where there are a number of farms, gets its water from aquifers that are at extreme risk of saltwater intrusion. This just means that the groundwater they depend on for fresh water is being inundated by coastal seawater and can't recharge enough due to lack of permeable surfaces. So what's needed is large-scale infrastructure upgrades to address this. But if you ever find yourself with dealing with saltwater intrusion, you can use rain collected water for irrigation or add gypsum to decrease excess salt in the soil and use compost and manure products with low salt levels. And the USDA also has more information and strategies for this as well. Next slide. And in terms of what climate adaptation looks like in New York City, the Plan NYC report details the city's sustainability initiatives and efforts to create a more climate adaptive city through the use of rain gardens, increasing tree canopy, active greenway, and resilient waterfronts. An example of that is the South Battery Park Resiliency Project, and this additional actually floodgates that were built where the Solar One project is on the east side of Manhattan. So those are just examples of climate adaptive innovation in response to the devastating impacts of Hurricane Sandy back in the fall of 2012. Next. And a great international example of climate adaptive innovation is this project. It's the largest climate project in the city of Copenhagen. And so this park is answering a need to handle the city's current and future challenges with water. So this is a park that offers an opportunity for recreation, exercise, both for every day in the case, and also in the case of extreme weather. So as you can see, the photo on the left shows what it looks like when it's completely filled with water. And then the photo on the right, it shows where there's this low wall that's been built around the perimeter to hold back around 14,000 cubic meters of water in the case of heavy rainfall events. Next. And just in terms of urban ag climate policy in New York City, the fact that the mayor's office of urban ag is housed under the mayor's office of climate and environmental justice, it speaks to the city's leadership in connecting urban ag and climate policy and viewing the benefits of urban ag through a climate resiliency lens, especially soil-based urban ag. The photo here on the left shows the three main pillars, which is Climate Smart Ag, which seeks to develop sustainable approaches to support the city's natural and built environment through scaled production, stormwater mitigation, and other climate resilience efforts on underutilized city-owned and land and green roofs. And the two photos on the right are the website for New York City Urban Ag and the most recently published report from the Mayor's Office of Urban Ag as well. And this QR code is a link to the NRCS Field Office Technical Guide if you want more information. But these are the 5 common agroforestry practices in the US. We mentioned before agroforestry being a tool for climate adaptation as there's rising heat and providing trees on farms provides that shading and cooling that crops need. So the 5 most common agroforestry practices are alley cropping, multi-story cropping, riparian forest buffers, silvopasture establishment, windbreak shelter belt establishment, and windbreak shelter belt restoration. So all these practices are, they're very diverse and they're not as simple in reality in these 5 categories, especially in New York City, but often people practice many types of agroforestry across the landscape and different practices over time. So essentially, taking a step back, agroforestry is the intentional integration of trees and shrubs into crop and animal farming systems to create economic, environmental, and social benefits. So we'll look at a few examples of that specifically in New York City. Next slide. So like I mentioned before, these are probably the most that we'll see in New York City, this multi-story cropping. And some of the purposes and benefits, like we mentioned, are improving the soil quality by increasing the utilization and cycling of nutrients and maintaining or increasing soil organic matter, increasing net carbon storage in plant biomass and soil. And then some of the benefits is that you're maximizing production in these forest systems, diversifying income, and a lot of times you see things like ramps or medicinals like ginseng and golden seal, but you could also have log-grown mushrooms, elderberry bushes, maple production. That's all examples of agroforestry practices. Next slide. This is Edgemere Farm in the Rockaways, and as you can see, they've shifted over from an annual vegetable cropping system to more of a perennial multi-story cropping system. And there's crops all underneath these plants. So again, these trees are providing that shading and cooling in times of extreme heat stress and just overall helping to mitigate the urban heat island effect. As we know, temperatures in the city tend to be higher than because of the pavement, the heat that's being absorbed in the pavement. So that's just something to keep an eye out and a strategy that can be incorporated. Next. Other climate adaptation strategies for urban farms include intercropping with mushrooms. So the photos on the left, red wine cap with asparagus. As we know, asparagus is more of a perennial crop. And by intercropping it with red wine cap mushrooms, you're helping to improve the water holding capacity in times of drought and also helping to look for additional water nutrients by extending the root system in the ground. The photo in the middle is NYRP. It's a mushroom farm in Inwood. And also Epistle Garden is, that's the greenhouse photo. And in those buckets, that's pink oyster mushroom. So the fact that there's extra space and that there's really high temperatures makes it a perfect spot for indoor pink oyster production. The photo on the right shows shiitake logs that are covered through shade cloth. So in the event of, direct sunlight, it's able to retain some of that moisture. But having either shiitake or oysters in a forest system helps to again maximize crop production in these urban forests. Next. Another example of agroforestry are these food forests. One in particular is with the Bronx River Alliance. And as you could see, there's a variety of different trees and crops, like, for example, white raspberry or uncommon fruit like chokeberry or aronia berries. And there's also just plantings under these trees as well. I actually hosted another red wine cap mushroom workshop, and having trees nearby that provide that cooling provides those co-benefits for both the mushrooms and also for retaining more moisture in the ground. And this is another international example. So this is an urban farm in Havana, and also another rural farm. So urban farms look very different in all parts of the world, but while livestock is limited in New York City, other countries like Cuba raise rabbits and goats in urban lots. And so this is an example of a tree species known as sabapul that provides high quality fodder for small ruminants and rabbits for this urban farm in Havana. So this is an example of climate adaptation because instead of relying on hay to be transported from outside areas, they can grow a greater quantity with trees. It's a perennial plant, similar to alfalfa. And the biggest benefit is that you're producing it there on site. So you don't have the monetary cost of transport. You're also protecting soil health since you don't need to till the soil in. And it also supports beneficial insects and pollinators and is just a great crop that is drought tolerant as well. And another example of a climate adaptation strategy, this is New Roots Community Farm, and there are various bioswales and rain gardens throughout New Roots Community Farm, and it makes it very adaptable in extreme rain events. A few years back, I think in 2021, there was a storm where there was nearby flooding, but the farm stayed intact and was able to act as a sponge to absorb all of that rainwater. And so having those rain gardens and bioswales really helps to capture and absorb that, and also just to reduce overall stormwater pollution. And next slide. Okay, so I'll hand it off now to Savannah, who will talk more about climate adaptation strategies for urban farms.
Thank you. Okay, so climate adaptation strategies for urban farms. So just calling back to what we talked about earlier, this one's kind of summarizing some of those findings for employee safety. So be sure to create a plan to protect personnel. Here are a few of the key risks summarized that we discussed earlier. But taking away from that, here are some emergency preparedness steps that we might implement. So one thing is having a communication plan in place, using text alerts, radios, etc., and having a clear chain of command can help you communicate your plans for what to do in case of emergency or what you're doing throughout the emergency situation. Additionally, designating safe zones for folks to go to if an event happens unexpectedly. Knowing where your shelters or safe zones are and communicating that to your employees is important. Then, like we discussed earlier, adjusting work schedules can be a key tool here so that you're working during cooling times of the day or safer conditions. Then having adequate supplies on hand to deal with these emergencies is important. So that means having and stocking a first aid kit, having water on hand, and then having adequate PPE. So that might look like insulated gloves in case of a cold event, waterproof boots if you're dealing with flooding or really wet conditions that also have good grip on the bottom so folks aren't falling down. But key takeaway here is it's important to conduct a safety assessment after extreme weather before you resume your work, before you allow folks to go back out there. But there are some resources to help you create an emergency or disaster preparedness plan. One of the really good ones is called Ready Ag from Penn State, and we're going to have a webinar later on that talks about disaster and emergency preparedness, so we can dive into this a little bit more deeply. So now we're going to switch gears and talk a little bit about soil health and why it's so important. So here's a figure that kind of exemplifies what we're going to get at about when we're talking about the importance of soil health. So when we have a healthy soil that has good structure, like the soil on the left, it's very porous. All the different crumbs and blocks fit together very loosely. There's a lot of space in here for roots to penetrate. There's space for water to infiltrate, and there's space for air exchange to occur. Versus less unhealthy soil over here on the right side, that is compacted and has poor soil structure. So what do we mean when we talk about unhealthy soil or soil that has poor structure? It might have a surface crust, like we see here. Surface crusting is especially bad if you are someone who direct seeds your plants. It can make it difficult for the seedlings to emerge from the soil profile. So you can see that occurring here. The seedling can't poke through the surface crust. You might have tightly packed crumbs, so there's not a lot of space for water to penetrate or percolate into the soil profile, and there's not a lot of space for gas exchange to occur, and roots are struggling to penetrate through here. And then you might have large blocky areas that have very few cracks for roots to adventure through. And then you can have the subsoil compacted layer that just kind of acts as a no-go zone for roots and water. So this is an unhealthy soil. plant's not thriving. We have a healthy soil, it's very loose, and the plant is thriving. So what are the factors that go into soil health? This is a great graphic that kind of helps you visualize this. So some techniques that we can undertake to improve soil health are minimizing disturbance. That means minimizing the amount of times that we are plowing, for example, or tilling, disturbing the soil in any way. It also looks like maximizing the amount of living roots that are in the soil. So when we are maximizing living roots, that means that the microbes in the soil have a plant to actively exchange metabolites with. In addition to that, the roots are holding all of our soil in place and providing an aerating benefit, because as these plants cycle through, they leave tiny little channels where their roots were, and they die off, and those are aerated pores that loosen up some of that soil structure. And then we have maximizing our soil cover so that we are reducing the amount of bare ground that can be exposed to loss either by extreme rainfall events or extreme wind events. Then we maximize our biodiversity in our cover crop mix, for example, or maybe in our cropping plan, so that we are providing feed for the soil biology. So you can think about this: minimize disturbance, maximize soil cover. That protects the soil by building soil aggregates, making habitat for organisms, and increasing soil organic matter. And then these two practices, maximizing living roots and maximizing biodiversity, act as feed for soil biology, which improves resistance and resilience to extreme events, and also helps to improve soil organic matter. So, just to go over that again, 3 principles here: providing adequate living cover is preferable, building our organic matter. This is usually not as big of an issue in urban soils. We'll talk about that why a bit later on. And then reducing our disturbance to preserve soil structure. So really the goal here is to make our soils as sponge-like as possible. So this is just a graph exploring the impact of soil cover on loss of soil to runoff, or the ability of water to infiltrate or runoff. So we have our soil cover on the bottom here in terms of tons per acre. Then we have percentage of precipitation that either runs off or is infiltrated into the soil. And you can see that when there's no soil cover, we have almost equal amounts of water running off as infiltrating. But when we go over here, we have very high amounts of soil covered. That increases the rate of infiltration from precipitation into the soil profile. So why is this happening? The cover on the soil physically prevents raindrop impact. So when the raindrop falls from the sky, it's not just bouncing off and then going off who knows where. When it's hitting that cover, the cover reduces the impact of that raindrop and allows it to kind of just sink into the soil. And then having cover on the soil physically slows runoff down and allows more time for that rain to infiltrate into the profile. So this is a great example of what that actually means. We'll see if we have sound. So I'm unable to get the sound going, but she's talking about the different treatments that we have here. So this is a rainfall simulation that's done oftentimes by the NRCS. The one on the left is bare ground, then we have sod. And then I think this middle one is like a crop that's been burned down, and then the far right's like a crop with stubble left in the field. So they have this rain effect, and you can just see all the soil running off into the jars on this bare ground plot, grass plot. We're not really losing any soil at all there. And I think this is a terminated cover crop, not entirely sure, but we'll link the video so you can go back and listen to it with sound. We're getting some soil coming out of that one. and then less soil running off here. So you can really see the impacts of these different treatments here. We'll make sure that you get the link to the video so you can watch it on your own time and hear all the great commentary that she has about this. But this is a common example done by NRCS and also by the Soil Health Lab. So I encourage you to go out and see it in person if you have the opportunity. So now we're going to talk a little bit about urban soil health more specifically. This is a great fact sheet that was made by Yolanda and Sam in partnership with our friends at New York Soil Health, Debbie and Joseph. And we'll make sure you get a link so you can look at this a little bit more on your own time. But some key takeaways from their findings are that urban soils generally have similar water holding capacity to the New York average soil. So why is available water capacity important? It is important because this is a soil's ability to hold water that's available to plant. And if you have lower available water, it can cause drought stress in your crops. And water is better held in firmer texture soils with high organic matter and high aggregate stability. Okay, and then we have soil organic matter, so that's plant-derived carbon present in the soil. Organic matter can increase available water capacity, form soil aggregates, among many other benefits. So you see here, this is where the huge difference really comes through. So urban farms tend to have between 2.9% organic matter and all the way up to 38.3% organic matter, which is huge. And why is that happening when compared to the New York average, which is really max 4% organic matter? That's because many soils on urban farms have way more compost added to them than soils on rural farms, for example. Some folks can even be growing in 100% compost. So that's why that soil organic matter number is so high there. And then moving on, talking about aggregate stability. So that's the soil's ability to maintain clumps. It's improved by microbial activity and is important for aeration, water infiltration, water storage, etc. We see that it's generally has a wide range on urban farms, so between 10.9 to 88.1%. And then comparing that to the New York average, that's 32.5% to 39.9%. So much smaller range on those generally urban, rural soils. And this just kind of reflects the diversity of soils that urban farms are growing in. Right? So like folks might be growing in 100% compost. They might be growing in their native soil. They might have bought in some type of soil mix that they've put into raised beds. So the key takeaway from this graphic is that generally urban soils are higher in organic matter than rural soils, and that urban soils are much more diverse than rural soils. So some of the things that might be rules of thumb for rural soils are not going to apply in the same way as urban soils, and we kind of have to tease those things out and think about them maybe a little bit differently. So we're going to move on to talking a little bit more about that. But one thing that I want to hammer home here, which I think, yeah, we're going to talk about that later on. But first off, organic matter, pH, are parts of the key parts of our soil that we like to monitor year over year in our constructed urban soils. We have some different physical differences in our constructed soils in terms of its ability to handle water, or how deep the soils might be, or how compacted they might be. And then we might have imbalances, nutrient imbalances that we might not see in rural soils. So we might have really high nitrogen or potassium, or I think that's manganese. And we might need to adjust the results of our soil tests for bulk density because, like I mentioned, a lot of these urban soils can have a lot more compost added to them, and they're a lot lighter. They have lower bulk density than rural soils. So that's going to impact the calibration of the soil tests that you get. And I think Sam has come up with some corrections for those. Not sure we can reach out to him and get some clarification on that. So key thing to take away here when we're talking about water handling is that how we discussed that a lot of these soils are very high in organic matter. Um, they have a lot of porosity, low bulk density. One thing to keep in mind when you have high organic matter is that when the soils are adequately moistened, they have really good water retention and are very well drained and have low compaction. But one thing that can happen when you have high organic matter and it gets dry is that those organic matter portions can become hydrophobic. So that means that they're not readily taking water up, and you have to kind of persistently moisten them until they're ready to become hydrophilic or draw water into those portions. So it's key. The adage is about watering deeply a few times a week might not play out the same if you have high organic matter urban soils. You might want to think about watering more frequently so you get around this problem of having hydrophobic soils. So one thing that can happen if you have these plants that are kind of water stressed, especially in tomatoes, is they can get some diseases or some issues like blossom end rot. Um, you can see that here. That's especially common in varieties like Roma tomatoes, for example. This can also be caused by low calcium in soils, but easiest fix is to increase your water and then think about maybe applying some type of calcium to get around this issue. But yeah, you can see that happening here. So, oftentimes our urban soils are a bit more shallow than rural soils. So that they increase the need for excellent water retention, right? Because we can't necessarily depend on the plants being able to access water that's deeper in the soil profile. We have a limited amount of water storage. Um, so some things that folks might do are to apply organic mulches like wood chips or straw to help seal that water in. Might cover crop creatively. So this is a buckwheat cover crop that's mowed and lightly incorporated on Red Hook Farm in Brooklyn, New York. And then you might think about reducing tillage to avoid disturbing your soil profile so that you're maintaining that sponge-like effect and the ability of your water to hold into the soil profile. So cover cropping is a great strategy to help reduce soil and erosion and improve soil health. It's also key in crowding out weeds, and it might help control pests and disease based off of the type that you choose. So some brassicas do help control pests and disease. So planting a mustard cover crop, for example, could be helpful there. And additionally, it increases biodiversity and provides pollinator habitat, especially if you're planting something like red clover. Um, are something along those lines, or you could choose to plant something like this is a daikon radish, which also has the moniker the tillage radish. It creates these huge holes in the soil profile when it grows right here that usually you plant these in the fall and then they terminate winter kill over winter. And then you just come back and there's huge holes all in the soil where it has loosened up things. These can also be used if you have a deeper compaction layer to try to break up that deeper compaction layer without extreme tillage. So here's a great video that you can access from, I think this is from NYBG or BBG, Brooklyn Botanical Gardens, but this is on turning in your cover crops if you're interested in how to do that in your raised beds. And then there's a cover crops for urban farms fact sheet that you can access here to talk a little bit more about cover cropping on urban farms. So, reduction in tillage is huge in terms of improving soil health. So why is that? It's because when you till, you disrupt soil structure, which leads to a cascade of impacts. Like we were talking about earlier, if you till a lot, that can lead to an increase in soil crusting. It can lead to a reduction in pore space. It can also cause that plow pan or that compaction layer to form. But there are some benefits of tillage, especially to urban farms who are growing organically. So it allows for more efficient weed control. Usually folks who are growing on urban farms rely on tillage or hand pulling or something along those lines to provide for all of their weed control. And it's also used to terminate cover crops that don't winter kill in organic systems. So there can be a lot of barriers to adopting reduced tillage on organic farms. And this is a survey that was done that kind of outlines what some of those reasons might be. And we can see that the fact that most people are relying on it for weed removal is probably the biggest reported barrier here. So one way to get around that is to tarp. So tarping allows for reduced tillage because it can sterilize the weed seed bank. You lay these black tarps over the soil gets hot and it can kill off some of those weed seeds that might be persisting in the soil, or they might germinate under this cover and not have anywhere to go and die off. But it can be logistically challenging to apply and keep in place, especially if you have a situation where you have high winds. And if you're trying to reduce your plastic, this is obviously a source of plastic on the farm, so there's some drawbacks there. Tarping can also be used to terminate cover crops that don't winter kill, so there's a benefit there. And if you're concerned about plastic waste, sometimes you can buy tarps. For example, a lot of farms upstate use silage, use these big black tarps called silage tarps to hold down uh, and ferment cow feed silage. Sometimes you can buy those secondhand to prevent them from going into the landfill if you're concerned about increased plastic waste. But here's a link to a tarping guide created by Cornell Small Farms that helps you understand everything you need to know about tarping, how to do it, how to source tarps, when to do it, all those good things. So this can be a really beneficial practice, especially if you're in a small scale urban farm. I feel like this is a great solution to help you reduce some of your tillage and help you take care of some of those issues, like weeds and terminating your cover crops. And mulching, very beneficial. It improves soil structure. It'll suppress weeds for you, helps prevent erosion, and can help to moderate some temperature extremes because it's holding some heat in the ground sometimes. And then additionally, it acts as seals to help keep in some soil moisture. But one thing to keep in mind, especially if you're mulching around trees, is to avoid the mulch volcano. Um, so you don't want to just pile it up all the way against the outside of the tree here. You want to be sure that the crown of the tree is still exposed if you're mulching, because what can happen if you're mulching around perennials and you get it too close to the bark is that fungal infections, fungus can start growing in this really moist mulch around the tree, and that can get into the bark and begin to affect, and it'll basically just girdle the tree. So that affects the ability of the tree to pull water out of the ground and up into its above ground tissues and ultimately leads to tree death. So being sure not to make a mulch volcano is very important if you're going to be mulching around trees or other perennials. And then irrigation management, very key. So installing something like drip irrigation will help you conserve water because that's a highly efficient form of irrigation. Installing soil moisture sensors can further improve efficiency because you're only going to irrigate exactly when you need it. There are high-tech ones like this one from Hobo that links to an app so you can see real-time soil moisture on your phone. There are lower tech ones that you just take out and you go and stick it in the soil and get a soil moisture reading. Or oftentimes folks are really in tune to when their crops need monitoring or watering. So you can just visually monitor if that works best for you. Another practice that's interesting and applied on some urban farms is the use of Oyas, which is a irrigation technique developed by indigenous peoples. And it provides consistent soil moisture around the Oya. So what happens is you take these terracotta pots, you bury them in the soil, and since these pots are permeable, water permeable, the water will seep from the pot out into the soil profile kind of gradually. So you can plant these around inside of your raised beds, for example, and then fill them up periodically, and that'll reduce your need for hand watering over time. All right. And I think that's all we had for today. So thank you for coming to watch this video. Please reach out if you have any questions or concern, and we really appreciate you taking the time to be here today.
Thanks so much, everybody. Take care.
Okay, cool.
Allison, do you want to hit that record?